In this video, we're going to talk about section 6.1, which is about composite functions. So in order to talk about composite functions, we need to know what a composite function is. So given two functions, f and g, the composite function is what we see below here, okay? This is the composite function, but we denote the composite function with f and then this O-looking thing, okay, and g, okay? You read the O-looking thing composite. So I would say f composite g, okay? And you define a composite function when you have f and then the O and the g, okay, as f of g of x. Okay, so remember I've got two functions, f and g, and so maybe to make it more clear, I could define some example functions down here, 2 plus 3x, and then g is 3 plus 5x, okay? So here are two random functions, and so f composite g is f of g of x, meaning that I place the entire function g in wherever the x was in f. Okay, so I know that that may seem kind of weird, but we'll get a lot of practice doing it. So other important pieces of information are that the domain of the composite function is the set of all numbers in g such that the whole function g is in the domain of f. Okay, again, probably confusing, but we will practice a bunch, and I promise it'll make sense. Okay, so let's practice or evaluate the following composite functions. Okay, and so the first one I want to look at is f composite g of 1. Okay, so again, this is new notation, stuff that we have not seen before. What we want to find is f composite g, okay, and then we're going to plug 1 in to the result. Okay, and so remember, f composite g, which looks like fog, I know, but it's not fog, it's f composite g, is equal to f of g of x. Meaning I'm going to take the entire function g and I'm going to substitute that in wherever I see an x in f. Okay, so my function f is 2x squared minus 3. Okay, and so I'm going to place the entire function g, which is 4x, in wherever I see an x. So let's do that. So f of g of x is 2 times, and originally in f it was just x squared, so now wherever there's an x I place the entire function g, so that's 4x, quantity squared minus 3. Okay, and so then I need to use my rules of exponents to evaluate 4x squared. Okay, when I have things in not in the exponent but in the sort of regular spot, I can't think of what you call that at the moment. Okay, and you raise it to an exponent, but the things in the bottom are multiplied, then the squared or whatever exponent goes to both of them, and so you have 2 times 4 squared times x squared minus 3. 4 squared is 16, and 16 times 2 is 32. So what I'm left with is 32 x squared minus 3. Okay, so that's f composite g. Okay, and then I need to evaluate that result at 1. Okay, and so I substitute 1 into this function here, and I get 32 times 1 squared minus 3. That's 32 minus 3, or 29. Okay? So that's how you evaluate a composite function. Now let's try another one. It might not always be f composite g. Here I have an example where it's g composite g. So I can do it with the same function. And so you would rewrite that as g of x. Okay? And so I substitute the entire function g wherever I see an x in g. Okay? Now I know that's probably a little confusing. It's a little confusing to say. But I start with my original function, which is 4 times something. And that something we replace with the entirety of g, which is 4x. Okay? And so when you multiply it out, that's 16x. Okay? And if you evaluate 16x at -1, which is what we want, so this is g of x. Okay? We evaluated that at -1. I get 16 times -1, or -16. Okay? So now let's give that a try. So you have a function f is x squared plus 3x minus 1, and g is 4x again. Okay? I want you to find f of g and g of f. You don't have to evaluate them, add a number, just find the composite functions.